Okay, so working through lectures and homeworks 17 through 23 this week, mostly about trig. In fact, I think it was all trig. Okay, so for those of you coming from a college algebra course or a high school algebra 2 course, this might be the first new stuff, right? This trigonometry stuff. Okay, so first in the homework is the button show work. Do you need to show your work? No, you do not have to show your work in Wiley Plus. Some people like to keep their work there because they like to keep everything electronically. You should have like a notebook or something where you keep all your work. That way, if you want to ask me a question, you can't figure out what you did wrong, I can look at what you already did. And it's always good to have a hard copy and not put your full trust in electronic things. Okay. Can you go over a shifted sine wave? Maybe something with a period other than 2 pi. Sure. Okay, so let's do 0. We'll have a period of 5. Good. Okay, and we'll say we have a high point at 1 and a low point and another high point at 5, because this is going to be sinusoidal, and we'll put a low point halfway between those two at 3, and then halfway between the high point and the low point it'll hit a middle point, so at 2 and at 4. Okay, so this is going to be one period of a sinusoidal function. All right, if I was going to write a formula for this thing, I probably should have used cosine. This is more of a shift of the cosine. Yeah, okay. So if I continued the graph that I had written there, sine would be a really easy choice because it already starts at its midline, right? So this was a bad example. I'm sorry. So we'll do a shift to the cosine function. So I'm going to write 2 formulas for this graph. First one is easier because there's no horizontal shift involved. When a function starts at its midline, at time 0, it's at its midline, sine is always a good choice. Okay? You can use a shifted cosine, which we'll do next, but sine is a good choice because it naturally starts at its midline and you don't have to do a horizontal shift. So I'm definitely going to use sine to start here. And then I have to put in the amplitude, so I have to add some values here. Let's call this 10 and 50, and so my midline's at 30. And my amplitude would be what? 20. Okay, should I use positive 20 or negative 20? Positive, because sine starts at its midline and goes up, right? If this was starting at its midline and going down, we would use the opposite of sine. Flip it over the x-axis. Okay, and then the period of this thing is 5, which is 2 pi over b, right? And b is the coefficient on x here. So b is 2 pi over 5. And there's no horizontal shift, so I don't have to worry about adding or subtracting within these parentheses. And then you just shift up to the midline. So you do plus 30. That shifts the whole graph up from the x-axis to the midline of 30. All right, but I could also write this as a cosine curve. Okay, so the early parts are all going to be the same period. But I'm going to have a shift. Right? So what I should do is I'm going to draw in, superimpose on top of this graph, a cosine curve that has a midline of 30 and a period of 5. Okay, so the cosine would start at a high point and finish at a high point. Oh, sorry, it's got a period. This thing's got a period of 4, doesn't it? It does. Period's 4. 2 pi over 4 is pi over 2. Okay, there we go. So cosine starts at a high point, finishes at a high point, hits a low point in between, and a middle point halfway between those two. Okay, so this is the cosine function without any shift. That's a cosine function that has a period of 4, amplitude 20, midline of 30. All right, so take this periwinkle cosine function. How do I have to move it to make it lay on top of the pink actual function? How do I have to shift it? Minus, yeah, I'm going to have to shift it to the right, which means I'm going to do a minus. How much? Give me a more specific number, not p. Like, exactly how much do I have to shift it? 1. Here to there. 1 unit. Have to shift it over 1. Okay, so this is going to be x minus 1. Minus because we're going right. Does that make sense? Okay, so these are two functions that have always the exact same y values, and we can just double check that they give us the right picture by using GeoGebra. Okay, 20 sine pi over 2x plus 30. All right, does that look like the graph of the function I sketched? Let's look at them side by side here. So there's my sketch. It has a high point at 1, and this has a high point at 1, and it's got another high point at 4, sorry, at 5, and this has a high point at 5. Okay, so this looks like the pink curve I sketched. And then we'll put in another formula and make sure that that also looks like it. So I'm going to put in g of x, which is 20 cosine of pi over 2 times x minus 1. And I put an extra set of parentheses in there. Oh, maybe not. And it's graphed right on top of the other. So you can see that those are the same function. Okay, so I'm going to graph this thing by hand. I could just dump it in GeoGebra and see what it looks like, but we'll do it by hand to try to like tell us what all these different pieces mean. So I've got the midline. I always start by graphing the midline first, which is at 4. So here's my axes, and then I'm going to put the midline at 4. All right. And then my amplitude is 5, so I got to go up 5 and down 5. So 5, 6, 7, 8, 9. And my low point will be at -1. All right, and what's the period of this thing? Pi, yeah, because it should be 2 pi divided by b, and b is this coefficient in front of the x. So this is 2 pi over 2, or pi. Okay, so I'm going to mark off, oh, this is a bad, let me just change this a little bit. There we go. I'm just changing the shift. Okay, so the period is pi, so I'm going to mark off multiples of pi on here. So let's do pi, 2 pi, that's good enough. And then this is pi over 2, pi over 4, 3 pi over 4. This is 3 pi over 2, 3/4 pi, and 5/4 pi. All right, so the sine function typically starts at its midline and goes up. In this case, we have a shift to the right pi over 4. So instead of starting at 0 at its midline, I'm going to start at pi over 4. And then if the period is pi, exactly pi units later, it's going to be back at its midline. So not at pi, but pi units from pi over 4. And then exactly halfway between those two, it'll be there. And halfway between the middles, we'll have a high and a low. And then we can sketch the sine function. All right, why don't you guys help me with this? What are some core concepts from this week? Radians, yes. Right? Another way to measure angles is a radian. Graphs of trig functions. Yep. Yes, inverse trig functions. The Pythagorean identity. What did you use the inverse trig functions for in several homework problems? To solve for theta. Yeah. Yep, solving equations. That have trig functions in them, right? For example, 4 plus 3 cosine 2 theta equals 1, something like that. Right? Solve that. Triangles. So we'll just call this solving triangles. right? I'll give you a triangle with several pieces of information, and I can ask for several other pieces of information. Anything else? Yeah, Riley? Yep, that's called the Pythagorean identity. That's great. That's okay. If you just better to know the equation than to know the name of it. Unit circle, yes. Yeah, so much of how you understand many of the things we listed here already is based on the unit circle. Yeah. I just thought of one and then it left my brain. I don't know. Anybody else have one? Yeah. That's a pretty good list. Concepts for the week. Okay, the amount of daylight varies over the course of the year. The summer solstice, which occurs on June 21st, which is the 172nd day of the year, is the longest day of the year. In Greenfield, there are 15 hours and 18 minutes of daylight. And then the winter solstice occurs on December 21st, the 355th day of the year. It's the shortest day when there are 9 hours and 5 minutes of daylight. So we want to model the length of the day in hours, d, as a function of the time t in days, where January 1st corresponds to t equals 1. January 2nd is t equals 2, etc. Okay, so here's my axes. So this is January 1st, 1-1. And then my high occurs on June 21st, which is the 172nd day of the year. So let's put this here. And then I have a low on the 355th day of the year. And then I also had a low. If this is January 1st, I have to go back how many days to get December 21st? 10 days, yeah. Well, we're just going to ignore that. We're going to ignore leap year for now. Yeah, so December 21st plus 10 days would actually make the 31st, right? So do I have to actually have to go back 11 days? Yeah, 11 days. Okay, so my low, my shortest day of the year is 9 hours, 5 minutes. So we'll put that here. 5 minutes is how much of an hour? Yeah, I need a calculator. How do I figure it out? 1/12, yeah. 5/60ths, 5 out of 60 minutes, right? Is 0.083, which is 1/12. 9 and a 12th, right? So typically when you're dealing with time, like this is a little wrinkle in every problem that deals with hours and minutes. Like it's really tempting to write 9.5 or 9.05, but that 5 is out of 60, not out of 10 or 100, because we measure time with 60s instead of 10s like everything else, right? So it's 9.083 repeating. And then the longest day is 15 hours, 18 minutes. So 18/60ths. 3/10. So 15.3 hours is the longest day. All right, so then to get the midline, I have to average those two numbers. Okay, so 15.3 plus 9.08 divided by 2. 12.1916 repeating. All right, so I'm not trying to write the formula. I'm not even trying to draw it yet. I'm just putting in all the important numbers on the axes. All right, now I'm going to try to draw it. Okay, so I have lows at -11, December 21st. And then again, the following December 21st. And I have a high halfway in between on June 21st. Okay, so that's one complete period. So I'm going to draw in my midline here. Okay, so halfway in between a low and a high, it hits a midpoint, but I need to know the value, the x value between halfway between -11 and 172. How do I figure out what number is exactly halfway between those two? Yeah, just take the average. Okay, so 172 minus 11 divided by 2 is 80.5. So 80.5 hits the midline. And I guess that's the 81st day, but a mathematical model is something that we take this mathematical thing and we try to make it match what happens in real life. Not always a perfect matchup. Okay, and then halfway between 172 and 355, 263.5. So these would be the equinoxes, right? Spring and fall equinox. Okay, so now I can connect these with a nice smooth sinusoidal looking curve. All right, so I'm supposed to model this thing. I need to come up with a formula, one using cosine and one using sine. Okay, so for me, based on what I've drawn, I immediately want to use cosine first, just because of the way I've drawn it. I started at a low and finished at a low, which means cosine, right? When you start at the middle, I tend to use sine. Okay, so based on what I have drawn, if I had just started here at the midline, I'd use sine, and I'll do that next. All right, so if I want to use cosine to model this, it's definitely going to have to shift because its low is not at time 0. So I'm just going to sort of put in the bones of a cosine function, and then we'll try to fill in the stuff. So we'll do the easy stuff first. What is the period of the, I'm sorry, what is the midline? 12.1916. You could use a fraction if you wanted. All right, and then the amplitude. You can just tell me how to get it if you can't do the. Yeah, I'm just going to subtract the high minus the midline or the midline minus the low. I need to know the distance from the midline to the peaks. So 15.3 minus 3.1083 repeating. Okay, and because I'm starting at a low, cosine function typically starts at a high, so this is going to be negative. Okay, so now I'll put in the value of b, which I derive from the period. What is the period of this function? 365 days. So my period is 2 pi over, sorry, b is 2 pi over 365. Okay, so cosine would typically start at a low point, right? So my cosine function would typically start here, or the negative cosine function would typically start here and move up, right? But I have to move that low point to the left 11 days. So how do I show that in my formula? Plus 11. Good. Maybe that is supposed to be a 10. What do you guys think? Because the whole thing is supposed to be 365 days. And we have 0 to 355. So that's 355 plus 11 would be 366. Maybe that should be a 10. All right, so does that make sense how we came up with the cosine function? All right, so let's do the sine function now. So I'll just put in the bones of a sine function. It's got the same midline. It's got the same period, so it's going to have 2 pi over 365. It's got the same amplitude, 3.1083 repeating. Now I just have to figure out the horizontal shift and whether or not I need a negative in front. All right, so if I'm going to treat this as a sine function, sine functions typically start at their midline. Okay, so this would be like my starting point. But since the sine would typically start here, I have to move it over to there. So how far do I have to move? How far would I have to shift a sine function to, instead of start here, start here? 80.5 to the right, right? I have to shift a typical sine function 80.5 units to the right. So I'm going to do minus 80.5. Oh, but if I change that to a 10, 162, it's actually 81 now. Okay. All right, and should it be positive or negative, my sine function? Positive, yeah, because I'm starting at the midline and heading up, which means positive. Okay. If we started at the midline and headed down, it would be negative. Okay, so we have a cosine function and a sine function that represent the same graph, the same phenomenon. All right, so there was a homework problem like where you had to identify functions as sinusoidal or not sinusoidal. So you do that just based on the definition of sinusoidal. And sinusoidal means the exact same behavior that repeats over and over again, right? So any function of the form sinusoidal. Okay. Tangent too. Okay, so any of those guys would be sinusoidal because the exact same behavior repeats every period. Okay. So it would look like a wave. You know, you have the exact same wave repeating every so often, right? Or if it was a tangent function, right, it would look like right, and the exact same graph repeats over and over and over again. You just keep redrawing it on a new period. All right, but it's possible to have functions that involve trig functions, but are not sinusoidal, right? So you could have something that looks like this, right? It's a wave. It involves a trig function because it's a wave, but it's not exactly the same over every period because its amplitude is getting bigger and bigger and bigger. I think this is y equals sine x over x, but let me double check. Or x times sine x. Let's see. Times. Yeah, it's x times sine x. So you can even think of that. I should have known that. You can think of the x as a varying amplitude, right? Instead of having a constant amplitude with a value of, say, 4, I'm going to have x be the amplitude, which means it's going to get bigger and bigger and bigger, right? So this is a trig function. It has sine of x in it, but it's not sinusoidal because the exact same thing isn't happening over and over again. Okay, so if you're not allowed to use a calculator, then you're definitely using a unit circle. It's the only alternative. Right, so we draw a unit circle. First thing I have to do is find 7 pi over 4. So I'm going to count off pi over 4s. I need 7 of them, right? So this is pi over 4. And I've drawn it so that I can just count pi over 4. So this is 1 pi over 4, 2 pi over 4, which is the same thing as pi over 2, 3 pi over 4, 4 pi over 4, which is the same thing as pi, 5 pi over 4, 6 pi over 4, which would reduce to 3 pi over 2, 7 pi over 4. Right here. Okay, what are the coordinates of that point? Yep, it's positive, negative, because to get to this point, you would go right and then down. So it's positive, negative, and it is 1 over root 2, negative 1 over root 2. So that's something that you should know, or you should have a copy of your unit circle with you all the time if you don't have it memorized. Some unit circles will say this is root 2 over 2. It's the same value. It's just the denominator has been rationalized. You know, just like you can write 1 as 5/5 or 1 as 0.9 repeating forever, you can write 1 over root 2 as root 2 over 2. They're the same value. Root 2 over 2. Nope. So if I have 1 over root 2, this is a process called rationalizing the denominator, and It used to be really stressed in math courses that you should always rationalize the denominator, but those were the days before we had easy access to calculators that could actually do 1 divided by root 2. In the days before you had a calculator in your pocket, if you wanted to come up with a decimal approximation for this, 1 divided by root 2 was a hard calculation to do. So instead, we would change this by multiplying the top and bottom of the fraction by root 2. Okay. That it doesn't change the value at all because you're just multiplying by a fancy form of 1. Okay. And then you multiply the tops and you get root 2 on top. 1 times root 2 is root 2. What is root 2 times root 2? 2. And then to do this division by hand, the square root of 2 divided by 2 was much easier than doing 1 divided by root 2 by hand. But if we're going to use calculators, it does not matter, right? So just need to recognize that these two things are equivalent. Know that they're the same thing, because you'll see them used interchangeably. All right, so now I want to find the secant. Okay, so the secant of any angle theta is the reciprocal of the cosine, right? So, and the cosine is the x-coordinate, so this is 1 over the x-coordinate, the reciprocal of the cosine. So the secant of 7 pi over 4 is the reciprocal of this x-coordinate, 1 over root 2. What is the reciprocal of 1 over root 2? Root 2 over 1 or just root 2? So writing 1 over something is the same thing as saying the reciprocal of that thing. Let me just do that out because it can be a sticking point. So 1 divided by 1 over root 2. 1 over the x-coordinate. So 1 I could rewrite as 1 over 1, right? And then dividing by a fraction is the same thing as multiplying by its reciprocal. 1 over 1 times root 2 over 1 is root 2. So you can do the division out if you want, or you can just flip the x-coordinate over. Okay, so the exact value of 35 pi over, of the secant of 35 pi over 6. All right, here's my unit circle. I'm going to put in pi over 6's. So pi over 6 is like 30 degrees right there. And then if I go another 30 degrees or another pi over 6, I would get 2 pi over 6, which is pi over 3. So I'm just going to put in the multiples of pi over 6 here, which is breaking each quadrant into thirds, basically, because these are 30-degree angles, so it's 30, 60, 90, right? Or pi over 6, 2 pi over 6, 3 pi over 6, which is pi over 2. All right, so here's pi over 6. I need to count off 35 pi over 6's. So I've got 1 pi over 6, 2 pi over 6, which is the same thing as pi over 3, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, which is pi, right? 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6, or 2 pi. All right, so how could I do this quickly without actually counting to 35? Yeah, so 36 pi over 6 would be 6 pi, which would be right here. But it's only 35 pi over 6, so I go down 1. That makes sense? Okay. So this angle right here, this is 35 pi over 6. And you could just count to 35. You could just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 24, 36, and then come back by 1 to be at 35. All right, coordinates of this point. It's going to be positive, negative, because you go right and down. Root 3 over 2, negative a half. Yep. So root 3 over 2 is longer than a half, so that's how I remember the orders of these coordinates. We went over more than we went down, so the root 3 over 2 comes first. Okay, so then the secant of an angle, just like in the last one, it's the reciprocal of the x coordinate, because secant is the reciprocal of cosine. So the secant of 35 pi over 6 is the reciprocal of the x coordinate, so that would be 2 over root 3. And that answer is perfectly acceptable. Some people are in the habit of rationalizing the denominator, where you would multiply the top and bottom of this fraction by root 3. So you would get 2 root 3 over 3. Those are the same value. All right. So what values of t does the graph of y equal tan t have vertical asymptotes? So you can just look at a graph of this thing to figure out where the asymptotes are. It looks like this. It goes right through the origin, and then there's an asymptote, and it repeats. Okay, so those asymptotes are at odd multiples of pi over 2. So this is pi over 2. This is 3 pi over 2, 5 pi over 2. So you can't just say multiples of pi over 2, because 2 pi over 2 is not an asymptote, right? It's a 0 of the function. So this is odd multiples of pi over 2. So it would be 1 pi over 2, 3 pi over 2, 5 pi over 2. All right, so you can just look at a picture of it to see where the asymptotes are. And then what can you say about the graph of cosine t at odd multiples of pi over 2? So let's take a quick graph of the cosine function. Starts at a high point, finishes at a high point, low point in between, zeros in between the highs and lows. So this is pi over 2, 3 pi over 2. So what happens at the cosine function at the odd multiples of pi over 2? They're intercepts, yeah. The y value is 0, x-intercepts. Okay, so that's why we have vertical asymptotes there. Because remember, tangent is sine over cosine. And if the cosine is 0 at odd multiples of pi, the tangent would have to be undefined, right? So the tangent is undefined when cosine t equals 0. So then we end up getting these vertical asymptotes because the function's not defined there. And as the cosine of t gets closer and closer to 0, the value of this function gets bigger and bigger and bigger, right? Because when you divide by something really small, it's going to go in a lot of times. So the fraction gets really big. All right. At what values of t does the graph of tangent t have t-intercepts? Okay, so let's look at our picture from part A. We've got 0, we've got pi, we've got 2 pi. So what does it look like? How would you describe where the x-intercepts are? Multiples of pi, yeah. Because 0 pi, 1 pi, 2 pi, the next one will be at 3 pi. So they're just multiples of pi. And then I think there was another part to this question. Let me see. Yeah, one more part here. Okay, so what can you say about the graph of sine t at multiples of pi? So let's sketch the graph of sine. Starts at its middle, finishes at its middle, it's its middle halfway in between, and in between those it's got a high and a low. So it's 2 pi, pi, pi over 2, 3 pi over 2. Okay. So at multiples of pi, 0, pi, 2 pi, what happens to the sine function? Intercepts, yeah. Y equals sine t is 0 at multiples of pi. So that explains why the tangent has zeros at multiples of pi also, because the tangent is the sine over the cosine, and when the numerator of a fraction equals 0, the whole fraction equals 0. So the sine and the tangent have zeros at the same place. Does that make sense? So tangent t is 0 when sine of t is 0. Okay, so we're trying to look at different reflections, putting the negative sign in different places in the graphs of sine and cosine. So let's start by just graphing the sine of x. So we've got middle, 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 high, low. Okay, so y equals sine x is done there in purple. So if I wanted to do the sine of negative x, that is going to be a reflection about the y-axis. So I put this in a bad spot here. Okay. So that's going to be a reflection about the y-axis. So I'm going to extend this. And if I draw the reflection of this about the y-axis, it's going to look like something like that. Right? Just reflect the whole thing about the y-axis. And then if I do, let's say in another color, y equals negative sine x. So that's a reflection about the x-axis, because the negative's on the outside. So that's going to look like this. And yes, yeah, I was just going to. So if I were to continue the green wave, it would go right into the pink wave if I went negative. So those two things are the same. Same graph. So what does it mean when a function, if you plug in the negative x and you get the negative y? What is that called? Anybody remember? Starts with an O, 3 letters. That's called an odd function, right? When you plug in the negative x and you get the negative y, that's called an odd function. So this tells us that the sine of x is an odd function. In other words, it has origin symmetry. Right? So if you were to do two folds over the x and the y, the two pieces of the graph would lay on top of each other. So let's look at cosine. Let's see if cosine has a similar property. So if I start by drawing cosine, It starts at a high, finishes at a high, goes like this. All right, so if I were to draw y equals the cosine of negative x, that would be a reflection over the y-axis. So it would look like that. But what is true about that pink curve? It's the same. It's just a continuation of the original purple curve, right? So these two things are the same. Cosine of negative x is the same as the cosine of x. Those are the same functions. Okay, so, and what's the name for a function that has this special property where if you plug in the negative x, you get the same y value? Even, yeah. So this tells us that y equals cosine x is an even function. There isn't a third kind, it's just even and odd. That's a great question. What if you have a function that's symmetric over the x-axis? For example, that. Is that a special kind of function? It's not a function, right? Why not? It doesn't pass the vertical line test, right? There's an input x that has two different outputs y. So this is not a function, which is why there's no special name for it. A power function looks like this: a constant times x to a power. Okay. And nothing else, right? It has to have this form: a constant times x to another constant. So if there's any other term, you're done. It's not a power function. A polynomial has the form a0 plus a1x plus a2x squared plus a3x. And those a0, a1, a2, those are just constants. Okay, they're just numbers. So the powers in a polynomial have to be integers: 1, 2, 3, 4, 0. They have to be integer. They have to be positive integers. So this is like a sum of power functions that has positive integer exponents. So part A here, f of x equals 4 times 12 to the x. Power polynomial, both or neither? Neither, because the x is in the variable is in the exponent. In a power function, the x is the base, right? It's x to a constant. So this is neither. This is an exponential function. All right, and then B, we've got g of x equals 4x to the 12th. What do you think? Definitely power function because it fits this ax to the b, right? It's a number times x to another number. Power function. But it's also a polynomial function because it's a positive integer exponent, right? Yeah. It would. The base would just be 4 to the 12th. I'm sorry, the coefficient would be 4 to the 12th. Yeah, so if I had written it like this, that's the same thing as 4 to the 12th times x to the 12th. So still a power function because you can put it in a x to the 12th form. Sure, you can, yeah, you can, but the reason that it's a power function is because you can write it like a number times x to another number. All right, so this is both power and polynomial. So a polynomial function can have as many or as few terms as you want, right? So what? 1, I guess. It'd have to have at least 1 to be a polynomial. Yep. So lines are polynomials, quadratics are polynomials, cubics, quartics, quintics, all polynomials. So this is both. And then number 3 is 1 minus 4x to the 12th. Now it's not a power function because it's got 2 terms. A power function can only have 1 term, ax to the b. So this is a polynomial. It's got 2 terms. The exponent is a positive integer. So this is a polynomial. And then the last one is the 4th root of 12x. Okay, which is the same thing as 12x to what power? The 1/4, very good. Which is the same thing as 12 to the 1/4 times x to the 1/4. So this is a number times x to another number. That makes this a what? Power function. But I'll just quickly show how to do it and not go through all the calculations. Okay, so this is supposed to be a power function that goes through these 2 points. And since you know very well now that a power function has this form, we're just trying to find what a and b should be to make it go through those 2 points. So you have 2 unknowns, and luckily we have 2 points. That means we can write 2 equations. So replace the y and the x with the y and the x coordinate from a point. And so I have 5 equals a times 1 to the b. But what is 1 to the anything, no matter what that thing is? 1. So this tells us 5 equals a times 1, so a is 5. So I now know one of my variables. I know y equals 5 times x to the b. Replace the a with the 5. Then you use your other point to figure out what b is. Replace the y. Sorry, that's 180. Replace the y with the y coordinate, the x with the x coordinate, and you solve for the b. So divide both sides by 5, you get 36 equals 2 to the b. When you have the b in the exponent, you take the ln of both sides. So the ln of 36 equals b times the ln of 2. So I took both answers, ln 36 over ln 2 or 5.17. So your final function is y equals 5 x to whatever you want to write b as, 5.17, or you can leave it as an exact ln 36 over ln 2. Number 4 was pretty good. Number 5 was pretty decent. And 6 was pretty good too. Yeah. So if you have questions about any others, the solutions are up online, so you can check out the solutions.